Hi everyone, welcome to the World Science Festival live chat with David Albert, who is a professor of philosophy at Columbia University and also a physicist. Today we're going to be talking about our recently released program, Pondering the Imponderables, the biggest questions in cosmology. We have a lot to talk about today, so please ask your questions into the chat box on YouTube and we will get to as many questions as we can. Kevin asks, would it be correct to say that whatever physics brought us into existence also brought life into existence?
That seems right to me. There was a period. There was a period in the history of the universe before there was anything like life or human beings, and if physics can really, at the end of the day, amount to a complete account of the things that it's supposed to be a complete account of the motions of material bodies. If that aspiration is taken really seriously, it's going to have to amount to something that can give us an account of how life first arose, of how we first arose out of life, so on and so forth. We have crude sketches from the work of people like Darwin and so on about how that might have begun to happen. But yeah, if physics really aspires to be a complete account of the behaviors of material things, among the material things that it needs to be a complete account of are not just rocks and planets and baseballs and projectiles, but plants and animals and people and so on.
I think that's a question that George Ellis, who is also on this program with you,
Right.
is looking at.
Right,
pretty
and George would
intensely.
have a quite different picture of it. That's right.
Yeah.
That's right. It's good that you bring him up. Yes, George thinks that George finds it very implausible that there could be a kind of physics that's complete in the sense that I was just describing. I very well understand the reasons for thinking such a thing. It's definitely true that the kind of mechanistic picture that physics ends up presenting us with of what kinds of things we are is very, very difficult to take in and very much at odds with our normal intuitions about what kinds of things we are. I think the question of whether physics can be completed in that way is sort of the basic question that the scientific project is investigating. George thinks that he sees clear arguments that physics couldn't be completed in the way I'm describing here. I don't understand why those arguments are compelling. We have intuitions about what we are, but we're used to physics overturning all sorts of very fundamental intuitions we have about the world. Whether it will succeed, whether it could ever succeed in reaching all the way to its goal in this respect is something we're going to have to wait and see about. That's what I take to be the fundamental question that the scientific project is addressing itself to. I guess I wouldn't, in advance of that, have such clear intuitions about it as George seems to have.
Interesting. So this next question comes from Hakeem Jahan Sek, who asks, how do extra dimensions play a role in understanding the universe? And kind of coming back to that first question, is there any progress toward experiments that could ever detect extra dimensions?
So, yes, there are a number of ways in which speculations about extra dimensions play an important role in the attempt to understand the physical world now. One that's very widely known has to do with string theory. In order for strings to be able to behave in ways that seem to plausibly be able to give rise to the kind of world we see, we need to imagine them as vibrating around in more than 3 spatial dimensions. There are other reasons coming from the foundations of quantum mechanics where you might think that sort of non-local connections that we've discovered between very distant physical systems might find their most plausible explanation in imagining that space has more dimensions than the 3 that we usually think it does. So there are a bunch of places where speculations about extra dimensions have come up. Of course, they came up also 100 years ago in the development of Einstein's special theory of relativity, where time came to be understood as much more like a 4th spatial dimension than anybody had suspected it might be before Einstein came along. And special relativity is, of course, now an extremely well experimentally confirmed theory. We're still groping for experiments that might be able to confirm or refute string theory for us, but people are hopeful that eventually we will be able to design such experiments. So, as you were saying, this connects up with the first question. Some of these experiments may be hard to do. Some of them may require a great deal of cleverness and ingenuity in order to set up situations which will tease some of these secrets out of nature. But I don't see a reason to be pessimistic in general that these things will have empirical implications that will in principle be able to probe by doing experiments.
It's interesting you bring up time as an extra dimension, because
Right.
I think these like 11 dimensions sound so weird, but
Right.
now with 100 years past, 4 dimensions doesn't feel weird anymore.
Yeah, 4 dimensions sounded very weird to people at
Yeah.
the time, and we now know very well experimentally what that means.
Right.
What you might call its cash value is in terms of experiments that we can actually do and effects that we can actually see.
Mm-hmm. So this is a very simple question with probably not a simple answer. Explain how order results from chaos in this world, please. Simple request.
Well, I mean, we have a number of really interesting scenarios, scientific scenarios. Maybe the most vivid one is the Darwinian picture of evolution by random mutation and natural selection. It was always the case that one of the most powerful arguments people could elicit for there having been an intelligent designer of the universe is the magnificent design of living organisms, which seems so efficient, so well thought out, so intricate, so well adapted to the jobs they need to do, that they seem to be vividly screaming out, testifying to the presence of some kind of intelligent designer. And there's this just sort of amazing idea of Darwin's, which is very simple but unbelievably powerful. That, look, here's an account of how all this order could have emerged from something much more chaotic without the intervention of a designer or anything like that. It could be just that there are random genetic changes going on in living organisms all the time, the vast majority of which are grotesque failures that don't contribute to the survival of those organisms at all and don't contribute to their ability to pass on their genes to successive generations. But there's a very, very small number which by pure chance result in mutations that increase the adaptability, the adaptedness of that organism to its environment, increase the efficiency with which it processes energy or information, increase its ability to defend itself against predators or something like that. And this isn't because anything was designed for their benefit. It's because when this comes along at random, it increases the ability of these organisms to pass down their genes to another generation. It increases their ability to survive. And so it can count as a successful explanation of why, if you look down the road, you see these ever-increasing complexities and degrees of organization in living systems, which it's fair to say emerged out of chaos without the intervention of any intelligent designer. We have other examples of emergence of order from chaos like that on more elementary levels in statistical mechanics and so on and so forth. There, it's a result of something in mathematics just called the law of large numbers, that if you that if you have a sort of random looking situation where half the time a certain particle goes one way and half the time a certain particle goes the other way, it looks just like complete chaos. If you look at very large numbers of particles, you'll see them as a result of that organizing themselves into two groups, one of which is this way, one of which is that way, which with very high probability have the same numbers of particles in them and so on and so forth. So there also you get the emergence of something that looks organized out of chaos, once again without the intervention of a designer, just as a matter of the way statistics mathematically compile with one another. So I think that's a really good question, and I think it's one of the great triumphs of the modern scientific project that we have been able to construct plausible, explanatorily powerful scenarios whereby things which looked as if they must have been designed with some purpose consciously in mind can have come to look that way without the intervention of any conscious intentions at all.
And this next question maybe goes to a very chaotic part of our world, the quantum world. It comes from I.A. Fleischer, who asks, what lies at the heart of the probabilistic nature of the wave function? What ultimately drives one outcome over another?
Well, I think it's fair to say that at the moment, that's an unresolved question. We have several ways of thinking about quantum mechanics now on the table. We have ways of thinking about these random events as associated with something called a collapse of the wave function. We have ways of thinking about these random events as things that depend very sensitively on initial conditions, which is the kind of thing that happens in classical statistical mechanics that I was just mentioning. We have ways of thinking about these random events as random shifts of our own perspective on the world rather than random shifts in the world itself. That's something associated with Everettian interpretations of quantum mechanics, Manyworlds interpretations of quantum mechanics. I think it's fair to say that we have several promising ways of trying to understand what this randomness is about and where it comes from. And luckily, various of these different interpretations are in principle experimentally distinguishable from one another, although we're not yet at the point in our technological development where we're able to do experiments that would distinguish between these interpretations. But there are, so the short answer to your question is we don't know. The slightly longer answer is we don't know yet, but there are several promising proposals on the table for making sense out of this. They make sense out of it in interestingly different ways that imply interestingly different basic metaphysical structures of the world, and we're doing the best we can. We're not nowhere with that problem. We have several proposals for understanding it, but we're very far from having definitively solved it.
And from our chat, Gaming Ball asks, what do you think about string theory? Do you believe in it?
I don't think of myself as particularly qualified I don't think I'm somebody who's enough of an expert on string theory for it to be of interest to anybody, whether I believe in it or not. I think it's and I don't see why there's a need to make a decision like that at this point. String theory has had all sorts of very dramatic triumphs in its history and a number of what might be regarded as setbacks in its history. It's a live research program. It's going extremely well in some respects and perhaps less well in others, and we're going to have to see how it plays out. The nice thing about science is that it's, scientific theories aren't things that we need to make up our minds about. Our minds get made up for us by the outcomes of experiments that we do. And before we've been able to do those experiments, I would think that the appropriate attitude is to be agnostic about it.
It's interesting, people ask if you believe in a theory. Do scientists, would they say that to each other, that, I believe in this theory?
I mean,
do you believe in
I
it?
think, I used to have a colleague in the philosophy department at Columbia named Sidney Morgenbesser, who used to make a distinction between believing that and believing in. To say, I believe that such and such is the case, is to say, you've amassed sufficient evidence to be relatively certain about this, and so on and so forth. To say I believe in quantum mechanics or I believe in string theory, I take it is something more like, not necessarily that I believe that it's true, but I believe this is a worthwhile research project, which is worth pursuing, which is worth expending energy on, which is raising questions which it's worth getting to the bottom of. In that sense of believing in, I certainly believe in string theory. That's something quite a bit weaker than something like believing that what the theory says is true. I don't think we're in a position to make a decision about that yet. But I do think it's appropriate to say, this is a project that I believe in. This is a project which we're not wasting our time by pursuing.
And this next user actually has another way of putting it. Their name is Vada Ann. Do you give any weight to simulation theory? Maybe you could say what simulation theory is.
I'm not sure I know what simulation theory is. I mean, there is a large project of trying to do calculations about the implications of various physical theories by doing computer simulations, and that this is a way of exploring the consequences of theories. This is a way of doing experiments that we can't actually do out in the world to see what the implications of certain theories would be. I think that's an enormously important tool. I'm not sure if this is what the questioner means by simulation theory, but if they mean simulation of theories, of figuring out what the consequences of theories are by doing computer simulations of certain systems, I think that's a very important tool. It's proven especially important recently in astronomy and cosmology, simulations of the formations of galaxies, so on and so forth. It's given us very clear answers about which theories seem to be on the right track and which aren't. So I think it's a very important tool if that's what the reviewer is, if that's what the questioner is referring to.
I wonder if, and I also apologize if I get it wrong, if they mean the theory that perhaps the universe is a simulation.
Oh, I see.
I see. It may be what you're asking.
That sounds
or maybe there's
right.
a third option.
No. Actually, I think you're right.
Okay.
I should have thought of that. So that's a really interesting question. I think that there's a lot to say about this, and I don't want to get into a really long discussion, but it does how shall I put this? You get into a funny cognitive position if you play the following game with yourself. You say, well, let's see, I have all these experiments that I've done or heard about or people have told me about. On the basis of these experiments, I have a certain set of beliefs about what the laws of physics are. The belief that these are the laws of physics implies, among other things, that computers could be constructed consistent with those laws that would simulate a universe like ours, where we wouldn't really be looking at the universe. And on the basis of that, I conclude that I may well be a simulation. What I think is worth noting about this kind of chain of reasoning is that the minute you decide that you may be or probably are a simulation, you can no longer claim that the things that you remember as experiments from which you learned facts about the laws of physics really were anything like that. What you're suggesting is that those experiments that you remember were simulations as well, so that they didn't really give you access to what the actual laws of physics are, so that they didn't really give you useful information about the probability that you could be a simulation in the first place. So I think these kinds of chains of reasoning lead to a situation which philosophers refer to as a cognitive instability. I think the usual chains of reasoning which lead to the conclusion that we're a simulation are cognitively unstable in this way, and I'm not sure they're to be trusted. But this is just the tip of the iceberg of a very deep and very interesting problem. And thank you for clearing that up. I think your interpretation of the question was right.
Well, yes. I hope so for the chatter. I always think, well, empirically it might be good to know. Regardless, I still have to get up in the morning.
That's
right?
true.
I still have to stand in the crowds.
That's true.
On the subway.
But we want to, we're involved with science because we'd like to know what's really going on.
Right.
Independent of its impact on our practical lives. Right.
And this next question, I apologize, I'm not sure how to pronounce this person's name. So they ask, what is the philosophical view of the non-existing center of the universe? If it expanded from a point, why isn't there a center?
Oh, well, let's see how to talk about that quickly. The idea is, or at least here's a sort of metaphor for the idea. Think of imagine being a two-dimensional creature that lives in the surface of a three-dimensional sphere, in the outer surface of a three-dimensional sphere. So this three-dimensional sphere, imagine it's expanding. It started in an explosion from the three-dimensional center of the sphere. But that center isn't located anywhere on the surface, and it looks to everyone sitting on the surface as if everyone else that they look at is moving away from them in a radially symmetric way, as if they are the center of the expansion. If you just picture a sphere, the surface of a sphere, like the surface of a balloon that's progressively being blown up, and you've drawn some dots on the surface of the balloon with a magic marker, as the balloon blows up, each of those dots is going to be getting farther and farther apart from all the others. If you're standing on any one of the dots, it looks like all the other dots are moving radially away from you, even though what's really going on, if you look at it from the higher dimensional, three-dimensional point of view, the surface of the balloon is just expanding outwards from this center in three-dimensional space, but that center isn't a point anywhere in the space that's accessible to these two-dimensional beings on the surface. Good. Take that picture, jack the whole thing up by one dimension. So we're sitting not on the two-dimensional surface of a three-dimensional sphere, but on the three-dimensional surface of a four-dimensional sphere. You'll get an idea of how it could be the case that the universe could have exploded out of a point, but that point is not to be located anywhere in what we currently call the space that we live in.
We actually started chatting about this before you arrived a little bit. Does this question have anything to do with infinity, in the sense that you can't be in the center of something that's infinite?
No, there are lots of questions of infinity that come up in connection with cosmology, but this kind of a situation can be realized in a perfectly finite way. Imagine a balloon that has a perfectly definite finite size, but it's getting larger and larger as time goes by. The center from which the balloon is expanding is not going to be part of the space that these two-dimensional creatures live in.
Right. So this next question I want to thank Amr Mohsin for asking, because I've always been curious about it myself. How is energy conserved in cosmological expansion?
I'm not sure that I mean, there's a couple of things to say about this. In general relativity, the meaning of the notion of total energy of the world, and consequently the conservation of energy of the world, is a very non-trivial business. So even the idea of asking whether conservation of energy is true or false under those circumstances is complicated. But let me put those complications aside for the moment and just say, if you have, say, an explosion in which a bunch of matter that's gravitationally, the pieces of matter that are gravitationally attracted to each other start flying outwards, the way the conservation of energy works is that as they fly outwards and their potential energy gets larger and larger, they slow down under the influence of one another's gravitation, so their kinetic energy gets smaller and smaller. And these two variations exactly balance one another, so that as the potential energy is getting larger because they're getting farther apart, the kinetic energy is getting smaller because their acceleration outwards is slowing down more and more. And so the total energy, which is the sum of the potential and the kinetic energy, remains conserved.
And so this next question is probably like, there are thousands of years of your field behind this one. Out of Outer Space wants to know, do you believe we have free will?
So that's a really complicated question. There are various attitudes in the history of philosophy toward what you might mean by freedom of will. There's what's sometimes called a libertarian conception of freedom of will, which seems to demand that there couldn't be any external laws governing what we do or what we decide, or so on and so forth. And there are much more modest notions of free will, going back to philosophers like David Hume, who think that all it means to say that I did something freely is not that whether or not I did it wasn't determined by the initial physical conditions of the universe, but a more practical sense of whether I did something that was in accord with my desires at that moment, or rather whether somebody was forcefully moving my hand when I did it, or something like that. I don't see any reason not to believe, I don't see any reason from physics not to believe in this more modest Humean version of freedom of will. I think there may be very profound threats from physics to a more libertarian conception of freedom of will. And I guess I go back and forth in my own mind as to which of those conceptions is really the one that we take ourselves to have when we're lying in bed at night and thinking about what we'd like to do the next day. So that's a question that I'm very puzzled about. I think there's a very real tension between what we've discovered about the fundamental laws of physics and our conception of ourselves as having something called freedom. And it's something that I continue to be puzzled about, and I don't want to pretend that I'm more sure about it than I am.
We had a program on free will at the World Science Festival several years ago, and the panelists who all study this from the brain perspective of physics kind of all spent the whole 90 minutes saying why all this evidence shows that we don't have free will. And then at the end, the moderator asked, okay, personally, as a person, do you believe in free will? And they all said yes. Right.
So one of the things you're supposed to do if you're a philosopher is not compartmentalize yourself into, in this way, and try to find a way of answering questions that's going to satisfy you you know, in all the possible ways you might be asked about it, and in all the possible contexts you might be asked about it. And I think it's very, very puzzling and hard to figure out.
So this question comes from KJ Runia. They, I guess, saw an interesting discussion between you and Sean Carroll. It said you had some thoughts on the notion of probability in the Manyworlds interpretation. Can you elaborate?
Yes, very simply, I think that the Manyworlds interpretation of quantum mechanics is an interpretation which makes it very hard to make sense of these familiar probabilistic claims of quantum mechanics that one of the earlier questioners was asking about. We think that quantum mechanics makes the world chancy, but on the Manyworlds interpretation, all the things that might happen for sure, so that the actual evolution of the world is completely deterministic, and that makes it difficult to understand what all this talk about chances could possibly be about. So I think there have been many interesting attempts to come to grips with this problem. Sean, who you mentioned, is the author of one such attempt. There are other attempts by people like David Deutsch and David Wallace. But I think it's a hard problem. I'm not satisfied with any of the proposed solutions that have been offered so far. I think it's hard to see in a fully deterministic picture of the world like the Manyworlds interpretation how we're going to be able to make sense of these chancy or statistical elements of quantum mechanics that are the ones we encounter in our laboratories when we go and do experiments on subatomic particles. So I think there's a real problem there. And that's what some of the conversation with Sean that I think the questioner is referring to was about.
And I think this came up with Alan on the program, but regarding the multiverse. So
yes, that's a little bit of a different one, but I think there are similar problems there. These multiverses are once again claims that all of these various different universes are definitely there. So questions about the probability we should associate with this or that universe are very hard to make sense of.
So this question comes from Shivam Shrivastava. I'm sorry if I pronounced your name wrong. What suggestions would you have for a physics undergraduate like this person on what to explore more thoroughly?
Well, there's a lot of wonderfully open questions in physics. It depends where your tastes take you. There's, you know, there are very interesting things going on in solid state physics nowadays. At the more fundamental level, there are very interesting things going on in string theory, and there are very interesting things going on at the sort of boundary, which is the place that I work, the boundary between theoretical physics and philosophy. There are a lot of questions about what the foundational structure of physics is, some of which we've been discussing today. I think those are very open questions and questions that are being very fruitfully pursued now as well. So I guess my advice is to go with whatever piques your interest. That's what you're going to be able to work hard at. That's what you're going to turn out to be good at. And that's where you'll be able to make a contribution.
What do you think you would do if you were a physics undergrad right now?
That's a good question. It was I guess that's a really good question. I guess there's a lot of, and this relates to our panel here, there's been an enormous amount of feeling of intellectual openness and intellectual experimentation going on in things like the foundations of cosmology and the origins of the universe. I think that might be something I'd be attracted to.
All right, and this question is going to take us sort of right to the edge of where a lot of quantum physicists are right now. So Gaurav Mandola wants to know, is space-time or are space and time fundamental entities? Or are they emergent entities from something more fundamental?
That's a really good question. We don't know the answer. I would say that there are, from several different quarters, tentative kinds of evidence pushing more in the direction of the necessity of thinking of space and time as non-fundamental, but rather emergent sorts of entities. These are really intriguing. It's really amazing that we're able to begin to develop pictures of how that could be the case, and we're able to reason with pictures of how that could be the case. I think it's much too early to say at this point, but I do think that if you had to point to trends recently, more and more reasons have emerged for suspecting that space and time as we know them may not be fundamental entities and may have to be looked at as emerging from some more basic structure.
This next question, I think, gets to a lot of the discussion on the program about the beginning of the universe. It's from Bob Aldo. Why should it ever occur to us that somehow nothing existing should be more or less likely than something existing?
That's a really good question. That's a really good question. I think this is something that goes much, much farther back in the history of human speculation than just science. The idea that there not being anything, so here are two different attitudes. Attitude one, the situation in which there's nothing is a special and privileged situation in the following sense. There being nothing doesn't call for an explanation, okay? Whereas there being something does call for an explanation. And so if you're going to understand the world in a satisfying way, you need to know how the something got there from the nothing, okay? Because the nothing is the thing that didn't stand in need of explanation. But you could take quite a different attitude, which is there not being anything, and there being a golf ball, and there being a planet, and there being a galaxy. All these things are just different states the world could be in, okay? And no one of them is any more a priori plausible than any other one. No one of them in and of itself is, demands an explanation more or less than any one of them. The world could have been any number of ways. Once again, there's a golf ball, there's a planet, there's a building, there's nothing, there's a galaxy, yada, yada, yada. One could take the attitude that all of these are possible states of the world, and that it's a mistake to insist on getting ourselves stories about how the world could have gotten there from nothing, as if nothing somehow has a special status vis-a-vis explanation, that it's the situation of the world that for some reason stands less in need of an explanation than any other particular situation of the world. So I think that's a really good question.
Our next one is a good follow-up to that. It's another question about nothing. So Nick Elge asks, what's beyond the walls of the universe if it's nothing? But if nothing doesn't exist, then what might be beyond
So
the
there
edge?
isn't, so think again of this image of the two-dimensional surface of a three-dimensional sphere. You have these two-dimensional creatures making their way around in this two-dimensional surface of the three-dimensional sphere. Look what happens to these creatures. If they walk in any direction in what looks to them to be a straight line for long enough, they never hit a wall, okay? But eventually they come back to where they started, okay? So their world, the space of their world is finite, okay? But not because they ever run into a wall, okay, such that they have to ask what lies beyond this wall. The manifestation in their lives of their space being finite isn't that they run into a wall, but just that if they walk long enough in the same direction, they find themselves back where they started. They find themselves returning to regions that they've already been to. And they notice that whatever direction they walk off in, after they walk a certain distance in a straight line, they find they've come back to where they started. So they conclude that the total amount of space in their universe is finite, but this is not because there's anything like a wall or a boundary. This is an amazing idea of how the world could be finite but boundaryless. And this is something we owe to Einstein and to his general theory of relativity, the first possibilities of imagining a situation like this.
So there is no restaurant at the edge of the universe.
Yeah, so there's no edge of the universe. Once again, think of these creatures. They just keep walking around. Everything is normal. There's never any sense of coming to an edge. What you come to is not an edge, but a place where you were before.
So we've got time for just a few more questions here. This one comes from Ishan Biohar. Do you think it is necessary to strive for complete theory, which is mathematically consistent with our notion of past, present, and future?
I don't think it's necessary, but I think that's what the scientific project does strive to do, and I think that's an interesting project to attempt. Often you hear people say that science, just like all kinds of other ways of knowing, involves a leap of faith, involves an initial act of faith that there is going to be such a description of the world. That's actually not the way I look at it. It seems to me that the question science is investigating is precisely the question of whether a project like that is, at the end of the day, going to be able to pan out. That strikes me as a really interesting question, one that I'm moved to investigate, and one that I'd like to know the answer to. So that's why this project appeals to me, not because it seems to me that there's any a priori necessity that such a project has to work, or that such a project is one that we're somehow obliged to follow. I think it's an interesting project to follow.
And from Rapturel, what do you think about the hard problem of consciousness? And also, just to follow up on that easy one, is it computable, and can it be derived in physics?
So I think the hard problem of consciousness is a really hard problem. It's hard for me to envision any physical development which would make it clear to me why the brain state associated with, say, seeing a red blotch in front of me feels to me the way it does, okay? I think there's a real kind of apples and oranges kind of problem there. Somebody wants to tell me that you know, a particular particle in my head going around clockwise corresponds to the feeling of green, and the particle going counterclockwise corresponds to the feeling of red. I can perfectly well imagine theories which will tell us that when the particle is going clockwise, I'm going to have green kinds of physical behaviors. Say I'm going to step on the gas if I'm in the car, or I'm going to utter the sound green, or something like that. But there's a further question, which is what people are referring to as the hard problem, of why it's that particular physical activity in my head which somehow gives rise to the greenness feeling rather than the redness feeling. It's very difficult for me to imagine how purely physical developments could give us a convincing answer to a question like that. And the hard problem of consciousness is one of the many very deep questions about the world that I'm very puzzled about.
So I think this is going to be our last question today.
Okay.
It comes from KJ Runia. What made you decide to go from theoretical physics to working on the philosophical foundations of physics?
So it was at the time when I was getting my PhD in physics, I had been interested since high school in exactly this borderline between physics and philosophy, or borderline is maybe not a good word, this intersection between physics and philosophy. In a way, I always saw theoretical physics as a way of doing philosophy, a rigorous, clear, logically demanding way of approaching very deep philosophical questions about what time is and what space is, and whether or not we're dreaming, and so on and so forth. So that's always what I was interested in. And I pursued an education in theoretical physics and got a PhD in theoretical physics. But at the time when I got my PhD, which was in the very beginning of the 1980s, fashions within theoretical physics were generally very hostile to these foundational questions. That's a long story, and it arose for all kinds of interesting historical reasons. But it did, and at the time, I mean, I worked for several years as a professor in physics departments after I got my PhD, but there was a sense in which the kinds of intellectual activity that were welcomed in philosophy departments were much more aligned with the sorts of things I was interested in at the time than the kinds of philosophical activity, intellectual activity that were generally encouraged in physics departments. I'm glad to say that in the 35 years or so since then, that attitude has changed a lot. And there are now many more people in physics departments who are focused on and intrigued by these fundamental philosophical questions than there were when I got my PhD. So the short answer is it was sort of a historical accident. It also didn't change that much the kind of work I do. I've always had a rule that when you go nowadays to conferences on the foundations of physics, about half the people at such a conference will be employed in a physics department and half will be employed in a philosophy department. And it's not easy to tell by listening to their talks which department they're employed in. And similarly, when I write a paper now, my usual rule is that if when it's done, it has more than 2 equations in it, I send it to a physics journal, and if it has less than 2 equations in it, I send it to a philosophy journal. And there's not much more of a difference than that. There is a community of investigators now of what people refer to as the foundations of physics, some of whom are in physics departments, some of whom are philosophy departments, who communicate very energetically and closely with one another, and who are really very much engaged in the same project. It's one of those areas where, and I think this is usually a welcome intellectual development, where traditional disciplinary boundaries are breaking down.
And that's kind of a recent change too, that this conversation between physicists and philosophers has really opened
right.
up, right?
I think that's right.
Yeah. Well, thank you so much for joining us and for this really interesting conversation.
Thank you for having me.
And thank you to all of our viewers for all of your fantastic questions. They were great, and I wish we could sit here for 3 more hours and answer all of them. Please stay tuned for more videos and chats on our YouTube channel, and if you'd like to get alerts on when we're going to have more, you can sign up for our email newsletter on worldsciencefestival.com, and you'll get an update anytime we post a new video, have a chat, things like that. So we really appreciate you joining us, and we'll see you next time.